Oh. Okay, so welcome everybody. Yes. Yes. Yeah, I guess so. Okay.
Oh, this one was good. The previous one. This one, no. The ones with the previous. No?
Yeah, if you could leave this one, right, leave this one on so people can see the board and then that one off, yeah. Okay, so once again, welcome everybody. And it is my pleasure to introduce Bob Oliver from Université Paris 13, who will give a talk on realizability of fusion systems. Over to you. Okay. Thank you. So everything I'm going to talk about today is joint work with Carlos Broto and Ron Levy, except, of course, for older work that's not due to any of us. Roughly, I mean, the main thing I want to talk about is, well, fusion systems and how they're realized by different kinds of groups. I'm going to be talking in general about fusion systems over discrete pictorial groups. I mean, is this button in the middle, is that a pointer?
No, I think that it will be a pointer.
I just don't want to press something that might.
No, here you have the thingy. If you change it, it will be a pointer.
Yeah.
And then if you want to go back to mouse mode, you go here.
Oh. Okay. Okay. Yeah. Anyhow, it's going to be centered around fusion systems over discrete pictorial groups and how they're, I mean, induced by finite groups and by compact Lie groups as those are the motivating examples. And then talking about abstract fusion systems and what it means for a fusion system to be realizable or exotic. In the case of fusion systems over finite groups, it's fairly straightforward, but once we go to infinite groups, that's less clear. Okay, anyhow, first thing I have to do is define what pictorial groups are before I can say what a fusion system over a pictorial group is. So P is always a fixed prime. Discrete P torus is a group that's isomorphic to a product of copies of Z mod P to the infinity. So Z mod P to the infinity, you can think of that as the union of the cyclic P groups, Z mod P to the N, with the obvious inclusions. Or you can just think of it as Z1 over P, the ring Z1 over P modulo the subring Z. Or you can think of it as the group of complex roots of unity of P power order. So discrete pictorial group, that's a group with a normal subgroup of P power index. That's discrete P torus. And in this case, for any discrete pictorial group, this discrete P torus of P power index is unique. It can be characterized as the unique discrete P torus of finite index, or even as the intersection of all subgroups of finite index in P. And what that means is that we have a discrete p-toral group P with identity component. So the identity component is given then. We can define its order as a pair of natural numbers. The rank of the discrete p torus and the order or the index of the discrete p torus inside of P. So a pair of natural numbers ordered lexicographically, and this allows us to say that if you've got a subgroup P contained in Q, a pair of discrete p-toral groups, then P contained in Q implies that the order of P is less than or equal to the order of Q, with equality if and only if P equals Q, just as you would expect for finite groups. This is sort of just a comment on the side. Most of which isn't going to come up at all later on in the talk. The only thing that I think comes up is the term P group, which I'll be using here to mean a group, each of whose elements has P power order for a given prime P. So that's just an extension of what P group means to the infinite case, to certain infinite groups or P groups. And in particular, it's easy to check that all discrete p-toral groups are P groups in this sense. And then a couple other terms. Group is locally finite. Actually, this is also going to play a role later. Group is locally finite if and only if each finally generated subgroup is finite. And then it's Artinian if each descending sequence of subgroups becomes constant. Sort of the opposite of Noetherian. And so then that's the proposition, which I mentioned here only to help motivate why this particular class of groups is interesting, or one reason why this class of groups is interesting is the group is discrete p-toral if and only if it's locally finite, Artinian, and a P group, and only if it has all three of these properties. Okay. Now, the real reason that we got interested in these is because of the way they come up in compact as subgroups of compact Lie groups. And in fact, when I was first looking at these groups with Ron and Carlos, we actually, this class of groups goes back to Dwyer and Wilkerson, who were looking at, they were, as far as I know, the first to look at discrete p-toral groups. They called it, I think they called it p-discrete toral groups, which term that I thought sounded horrible, so just permuted the words. Okay. So the next slide, so this proposition, more or less what told us that it's probably not worth looking for a larger class of groups for what we want to do for constructing our fusion systems. But anyhow, you've got a compact Lie group, maximal torus T, S, subgroup of elements of P power order in T, then S, or S naught, then S naught is a discrete P torus whose rank is equal to the dimension of T. That's easily seen. And then the properties are key properties that you've got discrete p-toral groups, subgroups, S inside of the normalizer of the torus with the property that S intersect T is S naught. And the image of S in the quotient, in the Weil group, and N of T mod T, that image is a CeLO-Phi subgroup of N of T mod T. So what you're looking at really is an extension of an extension of S naught, this discrete p torus inside of the maximal torus, an extension of that by a CeLO-Phi subgroup of the Weil group. And then so the result is that there are such subgroups of normalizer of the torus. Any two of them are conjugate in G. And in fact, I remembered after writing the slide that they're actually conjugate in the normalizer of the torus. And then if P is an arbitrary discrete p-toral subgroup of G, then it's G conjugate to a subgroup of S. So that these subgroups have all the properties that one wants of CeLO subgroups. And we just call them the CeLO-Phi subgroups of G and let CeL sub P of G be the denote the set of all such subgroups. Okay. Now, fusion system of a group. So I wrote this abstractly because for now, I'm just talking about, especially about the fusion system of a compact Lie group or a finite group is a special case of that. But later on, I'll want to talk about fusion systems of certain discrete groups, infinite groups. So G's discrete or compact Lie. No, Lie group, compact Lie group. S, discrete p-toral group with the property, well, with this CeLO property, just that every discrete p-toral subgroup of G is conjugate to a subgroup of S. So then we define the fusion system F sub S of G to be the category whose objects are the subgroups of S, and where all pairs of subgroups P and Q. You let Hom sub, well, morphisms from P to Q in this category are all morphisms, homomorphisms between the subgroups that are induced by conjugation by elements of G. So this is what's called the fusion system of G, or with respect to S, or the P fusion system of G. And the idea is that it sort of gives a tool for encoding the P local structure of G, meaning where P local structure is a term used by the group theorists to mean CeLO structures and conjugation, G conjugation among subgroups of a CeLO subgroup. Okay. And then, yeah.
you have.
Well, that depends on what you want to do with it. No, you can, when working with compact Lie groups, you can look at either discrete p-toral groups like I'm talking about here, or p-toral groups, which are groups that are an extension of a torus in the ordinary sense by a p group. So that's what's often called a p-toral group. That's used, I mean, I use that a lot when constructing group actions of compact Lie groups on certain spaces. But it's got the disadvantage that not all subgroups of a p-toral group are p groups. Not p-toral. Well, you've got, take any other prime q, you've got, take all, I mean, inside of T, you've got a lot of elements of order q, or elements of infinite, well, anyhow, you can take finite subgroups of order prime to p inside of T and things like that. So when working, so that's what convinced us that it would be, for these purposes, it would be by far better to work with the discrete p-toral groups. And I think that's what convinced Dwyer and Wilkerson to look at them as well. And if you take the classifying spaces, so of a p-toral group, and then a discrete p-toral group inside of it with the same rank and so forth, they have the same, their p-completed classifying spaces are homotopy equivalent. So from certain points of view, it doesn't matter. And it's just a question, yeah, I mean, sometimes you need one, sometimes you need the other. Well, we've not invented one yet. I think you'd run into problems. Because first of all, you wouldn't be able to just say, take the category of all subgroups of S if you've got a lot of subgroups that look nothing like p-toral groups. Yeah. Okay. So in particular, this all works for compact Lie groups. Then and when looking at fusion systems of finite groups, that's what this is what motivated Pooch in the 1990s to define abstract fusion systems. And so that's what I want to talk about now, but going directly to the case of abstract fusion systems over discrete p-toral groups. So now defining a fusion system is easy, well, straightforward. You've got, given a discrete p-toral group S, fusion system over S, category whose objects are all subgroups of S, and where, so for each pair of subgroups, first of all, the morphisms in F from P to Q are all injective homomorphisms, and it includes all homomorphisms induced by conjugation in S. And then the second condition is that if you've got a morphism between it, then its inverse is also in the category after you restrict it properly to get an isomorphism of groups. So basically, what the second condition says is that, or in particular, it says that if you've got an isomorphism of groups in the category, then its inverse is also going to be in the category. Now, next thing is just notation. The upper F is the set of subgroups isomorphic to P inside the category F, or what we usually just say is just conjugate to P, F conjugate to P. Now, so far, these conditions are not restrictive enough. So our main objects of interest are the saturated fusion systems, which satisfy the additional axioms first formulated by Pooch for finite S, and motivated in part by Selov theorems. And just to mention it here, that for each compact Lie group G, in each S, Selov P subgroup of G in the sense mentioned earlier, the category Fs of G is a saturated fusion system over S. So, which will make sense, statement that will make sense once I've defined saturated fusion systems. Well, I hesitated whether or not to make a slide containing the definition. If you've not seen the definition before, I'm including it mostly just to give you an idea of its flavor. But I can promise you that none of these axioms will play any role later on in the talk. So gives you a quick idea of what's involved, what sort of conditions one puts in there, but none of it is going to be used later. Okay, so now we're looking at take arbitrary saturated fusion systems over discrete p-toroidal group S. And when S is finite, we say that F is realizable if and only if it's equal to or isomorphic to the fusion system of a finite group over one of its Selov subgroups. So writing it down the easy way here, F is realizable if F is equal to F sub S of G, fusion system of G over S, for some finite group G with Selov subgroup S. Conditions are important because various people have shown that any saturated fusion system, maybe any fusion system, I think any fusion system over a finite P group S can be realized by an infinite group, some infinite group, with respect to a Selov subgroup. And can also be realized by a finite group with respect to a P subgroup that might not be Selov. So both of these conditions are important. And I'll try to remember to get back later to the question of why we put in these conditions to call it realizable. Well, part of the reason is in the next paragraph. For topologists, these are realizable in the sense that, well, each saturated fusion system over a discrete p-toroidal group has an associated classifying space. And there's not time here to define that, what it means. I mean, that's one or more talks in itself. I can say that one way, there is a few different ways of defining the classifying space of a fusion system over a finite P group or discrete P-toral group. One way is as a certain associated, well, the nerve or P-completed nerve of a certain associated category. And then if S is finite, in fact, if S is finite and is realized by the finite group G, then the classifying space of F is homotopy equivalent to the P-completed classifying space of G of the group. And this is true more generally for compact Lie groups. If you've got a compact Lie group G, F is the fusion system of G with respect to a CELO subgroup, then BF, the classifying space, is homotopy equivalent to BG P completed. So this is an additional reason that makes them interesting. So now the question is, we have infinite discrete P-toral groups, and if F is a saturated fusion system over such a thing, what does it mean for F to be realizable? So we originally defined fusion systems over discrete P-toral groups as motivated by trying to get fusion systems of compact Lie groups just a minute. Wait. Yeah. Pressing a button that I didn't know would do anything. Yeah, so originally we were looking at compact Lie groups and fusion systems of compact Lie groups, and also of P-compact groups for those of you familiar with them. But that seemed all too restrictive when talking about what realizability should mean. So instead, we define realizability in terms of a certain class of discrete groups that I'll define now. Okay. So first of all, maybe I should say that it's groups that we've been calling LFS of P groups. If you think it's a horrible name, I agree with you. So anybody who has suggestions for a better name, please mention them while I'm here. LFS is short for locally finite with CELOs. And then P is necessary just to make it clear that it's all with respect to the prime P. So it's a group, they're groups that satisfy three conditions. First, they're locally finite. Remember, that means that every finally generated subgroup is finite. All P subgroups of G are discrete P-toral. And then the third condition is the sort of subtle one or messy one. For each sequence, increasing sequence of finite abelian subgroups of G, well, their centralizers in G become constant. So there's some n so that Cg of AI equals Cg of An for each I greater than or equal to n. And sorry?
What was the reason at the third condition?
Because it's needed for the next proposition is one reason. It turns out it's needed to get very far at all. I mean, we were discussing it, and I may get back to that later, but it's the first two, well, probably a little too complicated to talk about. Maybe at the end of the talk, I can say a little about it if people want to hear it, or else I can talk to you later in the week. But we've been looking at the class of groups you get with just the first two, and it's looking like it's possible if you extend the notion of being conjugate and you extend the notion of, extend the idea of the class of groups you're looking at, or well, no, the morphisms, and you have to enlarge the fusion system, otherwise it won't be saturated, so forth. Anyhow, things get very messy very quickly, and so we decided it made more sense to stick to, well, to include all three. Now, whether or not conceivable that there's some weaker condition that can replace this, I don't know. Anyhow, the proposition, which very strongly requires that third condition, is that if you've got an LFS of P group for some fixed prime P, let CLOF sub P of G be the set of all maximal P subgroups of G, then for each CLOF subgroup, you have first that every P subgroup of G is conjugate to a subgroup of S, and the fusion system is saturated. And in fact, and also this condition, topological condition, that the classifying space of that fusion system is homotopy equivalent to BGP completed. So you've got all of the conditions you want here. Now, without the third condition, I get one thing I can remark right now is that there are examples, a lot of the group theoretic side of this for the infinite groups is not due to us, is due to various group theorists working with infinite groups and locally finite groups. But you take the set of all maximal P subgroups of G, if you only have the first two conditions, then they don't even have to be isomorphic to each other, much less conjugate. So that right away tells you that things are going to get messier. Okay. But anyhow, with all three conditions, you get what you want. CLOF subgroups are conjugate to each other, and you get a saturated fusion system. Okay. Now there's a slightly smaller class that I want to talk about, the linear torsion groups, which is easier to define and easier for when constructing examples. So linear torsion group meaning all elements have finite order, and linear just means isomorphic to a subgroup of GLN of K for some field K. And so we'll be talking about characteristic of K, or that plays a role now and then. So we talk about linear torsion groups and characteristic P, meaning that they're contained in a general linear group over a field of characteristic P. And of course, many of the groups, like every finite group is a linear torsion group in every characteristic. But it turns out that there are also lots of linear torsion groups that are linear only in one particular characteristic. For example, let me just note one example. Take G, let G be the group of complex roots of unity. So and then G's, well, so obviously it's a linear group in characteristic, well, obviously it's a torsion group and it's linear in characteristic 0, but it's not linear in any positive characteristic. And I'll leave that as an exercise for now. Not terribly deep result. So it's not, let me just write that, G, A, if, and characteristic A, not 0. Okay. So now the proposition is that, and the result that makes this relevant is that for each prime P, G is a linear torsion group in characteristic Q for Q different from P, including possibly Q equals 0, then G is an LFS of P group. And let me just note that in particular, GLN of FQ bar is a linear torsion group in characteristic Q, and so that's locally finite LFS of P group for all P primes P different from Q. So in other words, if you look at things that are linear, contained in a general linear group over the algebraic closure of a finite field, then they're automatically torsion groups. If you're looking in characteristic 0, at infinite subgroups of infinite linear groups in characteristic 0, then it's not always clear how to arrange that they're all torsion. But in positive characteristic, it's straightforward. And of course, then this applies to all subgroups of a general linear group. So that's just to say that it provides a simple way of constructing examples. Straightforward. Okay. So based on these results, we define a saturated fusion system F over its discrete p-toral group to be realizable if it's isomorphic to the fusion system of some LFS of P group G with respect to a CELO subgroup. And we say that it's exotic if it's not realizable. And so now it gives rise to several questions, which is what I want to talk about during the rest of the time. So, first of all, natural to ask if you've got a F is fusion system over a finite P group, and it's realized by an LFS of P group, is it also realized by a finite group? And turns out that the answer is yes. In other words, we don't get any new realizable groups or realizable fusion systems over finite groups this way. Then fusion systems, compact Lie groups, are they all realized by these groups? Or are they all realizable in this new sense? And then the answer to that is also going to be yes. And then, so I'll briefly discuss these two questions in the next slides, and then spend most of the rest of the time talking about the third question. How does one prove that a fusion system over an infinite discrete pictorial group is not realized by any LFS of P group? In fact, this was the question that we were asking ourselves when we started on this particular project, meeting in Barcelona in January, and started off, I certainly had no expectation of getting anywhere, but then somehow we asked the right questions, combined the right answers, and it worked. And then the last question, they're a fusion system realized by LNF and LFS of P group, but not by any linear torsion group. In other words, what do we gain, if anything, by looking at this larger class of groups? And we don't know the answer to that, to the last question. We don't know any fusion system realized by an LF by a group in this larger class, but not by any linear torsion group. But we see no reason why there shouldn't be such examples. And in certain ways, it's easier to work with this larger class. Well, we do. I mean, in the finite case, we've got lots of, well, no, okay. I think you're talking about something else, because you're talking about the third question, right? Yeah. In the finite case, I mean, if you assume the classification of finite simple groups, then we have lots of examples where we know that they're exotic, that they're not realizable by any finite group. Yeah. Well, no, that's not the question I'm asking. I'm just asking for individual fusion systems over discrete, because when we started this project in January, we knew of no examples where we could prove in any way, I mean, no particular case where we could prove in any sense that they couldn't be realized by linear torsion groups. Now we have lots of examples, yes. Yeah, well, okay, because the other way is clear, since finite groups are special cases of LFS of P groups, yeah. So, yeah. Okay, well, I guess that's what I'm getting to next. Okay, so the proposition says that if F is a saturated fusion system or a finite P group S, and realized by some infinite group G, LFS of P group G, with CLOF subgroup S, then there is a finite subgroup that also realizes it. Finite subgroup of G that also realizes it in the more strict sense. So in particular, G naught has to contain S. And the key thing to remember is that these groups we're looking at are locally finite. So any finite set of elements is going to generate a finite subgroup. And that's what we do. We have to have S itself in there. The category F has only finitely many morphisms. So we choose one element of G that induces each morphism of F under conjugation. And then so that the finite set, the elements of S together with these elements, and then together they generate a finite subgroup G naught, which has the same fusion system. And it's easy to check that it has the same fusion system because by construction, F is contained in F sub S of G naught, and F sub S of G naught contained in F sub S of G. And since the first is equal to the third by assumption, then, well, it's over a finite P group, and you've only got finitely many subgroups, and finally many morphisms between any pair of subgroups, yes. Okay. Okay, so that part's straightforward. And so we have, it doesn't, so this doesn't help us at all in realizing finite fusion systems. The answer to the second question, I'm waffling a bit here. Likely to be yes, but we've only written down the proof in the connected case. And so the theorem is, well, the question was, you've got a compact Lie group G, is its fusion system at the prime P also realized by a group in this class of discrete groups, one of these discrete groups? And if G is connected, then the answer is yes, by a theorem, basically the theorem that goes back to Friedlander and Miesslin. Because, okay, just getting technical here, G is a reductive group scheme over Z. Well, group scheme is basically a functor from commutative rings to groups that sends, well, it satisfies certain conditions, but in particular, it sends algebraically complete fields to algebraic groups over those fields. And then, anyhow, reductive condition, that means basically it's a torus cross a semi-simple group or a central product of such. And so every compact Lie group is Well, let me just write down the, we've got, I mean, you've probably seen, or many of you have seen that every compact Lie group, or let's say connected to simplify it, is a maximal compact subgroup of some algebraic group, or of some complex algebraic group. So for example, UN is a maximal compact subgroup of GLNC. And so what that means in this case is that UN and GLN of FQ bar for Q a prime different from P, that they have isomorphic fusion systems at the prime P. And the proof, I think there's probably a direct algebraic proof of this, although I've not tried to write it down. But the proof we use uses the Friedlander-Miesslin theorem that says that the P-completed classifying spaces are homotopy equivalent. And then a whole bunch of people showed that the P-completed classifying space determines the fusion system. And so that's how we get that their fusion systems are isomorphic. Okay. So now getting to the third question, and then the one that you were asking about, how to prove that certain fusion systems are exotic. So back to what we were saying earlier, the case of a fusion system over a finite P group, in almost all cases, we prove that it's exotic by using the classification of finite simple groups. Or, well, whether you consider that a proof or not, that's how it's done. The only way we know how to do it. So more precisely, we first show that if F is realized by a finite group, then it's realized by a finite simple group or almost simple group. And of course, that this technique applies only to certain kinds of fusion systems, but somehow the ones we were looking at usually end up in this way. So if it's realized by some finite group, it'll be realized by something very close to a finite simple group. And then you just go through the list of all finite simple groups and check that none of them fit properly. So obviously, we can't do this in the infinite case because we've got no classification of simple LFS of P groups or even of linear torsion groups. And no expectation that there ever will be one. So instead, F is realized by the infinite group G. We filter G as a union of an increasing sequence of finite subgroups. So that's the new idea that we had this time. And so this works only if G is countable, but that can always be arranged by the using the following lemma. Got a saturated fusion system F over a discrete pictorial group S. If it's realized by an LFS of P group, then it's realized by a countable LFS of P group. And the proof of this result is basically the same as the proof that used earlier to show that if you've got a finite fusion system realized by an LFS of P group, then it's realized by a finite subgroup of that. If every saturated fusion system over a discrete pictorial group had only countably many morphisms, then it would be exactly the same proof. Well, that's not true, but it's generated by a set of countable set of morphisms. It's not true because it's got uncountably many subgroups. So uncountably many objects in the I think I have to go back and look, but I think as soon as you get a rank 2 discrete P torus, then you can get. Well, I don't think I ever wrote down the proof that it's uncountable, so maybe you'll prove me wrong. But I think it is. I convinced myself that it's uncountable. That there are sort of. I mean, you end up showing that this set contains 2 to the infinity, basically. I mean that there's a situation where you have to make infinitely many choices between 2 possibilities, and any combination of those choices will give you a subgroup, something like that. Okay, exercise. Okay. So anyhow, we can always assume that our subgroups, our groups are countable. And then, so then the idea is to filter it. Well, first, here's just a side remark. The lemma says that got a fusion system or a discrete pictorial group, identity component T, we think of as a maximal torus, even though it's a discrete P torus, not a torus. And assume this additional condition that T is its own centralizer. In other words, that there's no element of S minus T, no element in the difference that centralizes T. And you write F as a union of an increasing sequence of saturated fusion subsystems over finite subgroups, S sub I. Then okay, so then let T sub I be the intersection, T intersect Si. Then phi large enough, you have this equality. Well, the important thing, this gets very technical, you can see, but the important thing is that aught sub F of T, which you can think of as the Weil group of this fusion system, the automizer of the maximal torus in the fusion system, that is reflected, that you can read that off, is repeated in these finite subgroups once I gets large enough. And so basically the idea is that we show that certain groups cannot appear in these automizers and hence can't be realized. Okay, well, I'll try to make that clear shortly. And then what I wrote down, the last 2 lines are just a more precise way of saying that. Here I just wrote that those 2 are isomorphic, odd Fi of Ti, isomorphic odd F of T, but one can say that more precisely. The isomorphisms are induced in a certain way. Okay, and so what we're going to do is we're going to assume that F is realized by some LFS of P group G, write G, and we can assume that G is countable. So write G as an increasing union of finite subgroups. And it's important to choose them so that S sub I, the intersection S intersect G sub I, is a CLIF subgroup. In other words, you need that each, yeah, okay. Those have to be CLIF subgroups of G sub I so that you can define these finite fusion subsystems, F sub I. And then it's easy to check that F is the union of these F sub I's. And so that's sort of going to be the procedure. Whoops. And it leads to the following theorem, which, okay. So the first part is sort of messy, but basically, I mean, the important thing is that there are a few basic conditions that need to be satisfied. And then either it's exotic or else aught sub f of t contains a normal subgroup of index prime to p of a certain form. And certain form is isomorphic to a product of copies of one of the things on this list. Okay. And so basically, this list comes from certain, I'll say a little more on the next slide, but certain automizers that appear in finite groups of Lie type. Okay, so that's the form of the main theorem we want. I think I'll just go, not going to say much about the proof, except that basically to repeat that we're just doing what was outlined. You find these G sub I's, and then you analyze. So the G sub I's, and you know it has to contain a large subgroup of T. So in other words, it has to contain an abelian subgroup of high exponent P to the n for n gets larger and larger. And you know what the automizer of that abelian subgroup has to be. And well, there aren't very many simple groups that have these properties, have such subgroups. That's the thing. In fact, it shows that, well, you reduce it to simple groups that are groups of Lie type and characteristic different from P, and we know what possibilities are left. Okay. So now, the last slide, just want to finish with basically one family of examples. First of all, just noting that the examples that we've been looking at, Ron, Carlos, and me, come from two different sources. First, from, well, I guess an earlier paper with Albert Ruiz, where we classified simple saturated fusion systems over discrete p-toral groups whose identity component has index p in S. So that's just one special case, which turns out to be possible to handle, but general enough to give lots of curious examples. And then second, p-compact groups, which I don't want to define, but some of you, I think, are familiar with them. And various constructions, classification by lots of people. But so more concretely, I want to take my example from that first dot, where we're looking at, so prime P And here for now can be any prime, even 2. Take a discrete P torus of rank P minus 1. And now we take an extension of that by a group of order P. And then the statement is that there is a simple saturated fusion system over a discrete p-toral group S, the fusion system unique up to isomorphism, such that S contains T with index P, and such that the automizer of T, aught sub F of T, is CP cross semi-direct product CP minus 1. So you can think of this as a subgroup of sigma P, the symmetric group on P letters, and equal to the symmetric group when P equals 2 or 3. And that's why cases P equal 2 or 3 are separate. So if P equals 2 or 3, F is realized by the compact Lie group, PSU of P, projective special unitary group, and also by the discrete groups, projective special linear groups, PSLP of FQ bar for Q of prime different from P. And then if P is greater than or equal to 5, F is exotic by our main theorem. And let me just note that I'll go back to the main theorem, because here aught sub F of T is CP semi-direct product CP minus 1. Here, one just has to check through the list. Says it has to have a normal subgroup of index prime to P. That means basically containing group of order P. It's a product of copies of one of the following, but none of these are, fit, at least for N, for P, 5 or more. None of these works, and so so those groups have to be exotic according to the theorem. Okay, I'll stop there.
Just last specific example, one of the
Whoops.
So this last concrete example is part of this.
Yeah, that's part of what I did with Albert. Right. Yeah.
You have a more general generalization theorem.
Not that I know of, no. I've not, it wouldn't surprise me if it can be done. In fact, I would expect that it can be done. Yeah. But this, yeah, okay, this gets, so I guess near the beginning, I was saying a little about, what we want, why we choose this class, and what we want from a class where we call things realizable. And as far as, so let's just look at the finite case. Okay, that's what you're familiar with, and lots some other people maybe, that you can show that every saturated fusion system. In fact, I think it's every fusion system over a finite P group is realized by some infinite group with respect to maximal, with respect to a Selov subgroup, a maximal P group inside of that infinite group. But okay, there are two problems. One is, in general, those groups don't have the right classifying space. Okay, but that obviously isn't going to bother the algebraists, the group theorists. But the other thing is that when I think about realizability, I want it to be realizability by a class of groups where we know that each group in this class gives rise to a saturated fusion system. And that's what's missing in a lot of these infinite examples, or in Sejong's thing, that you get not only all saturated fusion systems, but all non-saturated fusion systems as well. And to me, anyhow, that makes it much less interesting. And so it was similar thing for choosing the class of groups we want to work with here. Well, partly, I mean, locally finite seemed like a natural condition to have. And at the very least, it's hard to do much of anything without the group being locally finite. They won't be locally finite, right? And they won't be torsion groups then either. And then, of course, the second condition that we were looking at, all P subgroups should be discrete P-toral. Well, we're looking at fusion systems over discrete P-toral groups. That's a natural condition to impose. So the third condition is the only one that's much of a question, whether that can be relaxed or not. And I can talk to you more about that later, but it gets fairly technical. But there's a way there. Let's just say that without that third condition, I think there's a way where you can construct a saturated fusion system from the group. It's not the fusion system in the sense that I described, but I think it can be done. Although at one point, I sat down and tried to write out the details of the proof, and it wasn't as simple as I had thought. So I have to emphasize, I think it's true, but I'm very far from certain. Yeah. But at the very least, it's going to be far, far more complicated. So that third condition also seems to be necessary to have. Yeah. Well, that was the context in which Dwyer and Wilkerson first started looking at discrete P-toral groups. I mean, they found them, if I remember correctly, I mean, they looked at both discrete P-toral groups and P-toral groups. And I think they found it useful to work with both. I forget the exact details, but yeah. But they do have, and then we showed in an earlier paper, well, in our first paper on fusion systems over discrete P-toral groups, we showed that each P-compact group has a as a fusion system, as a saturated fusion system, which can be defined. I mean, obviously it has to be defined using homotopy theory, but yeah, which can be defined.
So my question is about finite case as well. So I think at least one can also talk about like block realizable, right? So it comes from a fusion
Yeah.
system of a block, for example, and then it will basically raise the question about the block exhausting block, correct? And does people like study the difference between the block exotic fusion systems and the exotic fusion systems and the like traditional ones? Are they any different from one another? Or do we have an example where we have an exotic fusion system in the traditional sense, but it doesn't actually, it does come from a block?
I think the answer to that is no, in the sense that no examples are known yet, but there's no proof. Radha Kesar is the one who has been specializing on that and worked a lot. So if you're interested in the question, write to her.
I was wondering that, like, I think he was talking about it, but I wasn't sure if there are actually any like updates on it, any examples.
Okay, well,
because you mentioned about
yeah. Well, she's looked a lot into it, and I'm not sure. I don't know what the current status is of that. Except I think I'd have heard if she found an example of an exotic fusion system that's block realizable. I think she or other people would let me know, but would let everybody know, because I think that would be pretty spectacular. But I don't know how far she's gotten to. I don't know if even I'm not even sure whether maybe there's a program to try to prove that all block realizable fusion systems are realizable, are group realizable. But if there is such a program, I don't think it's been carried out completely, but I don't know whether she sees hope of showing that or not. No, because they're all based on the classification. Yeah, I mean, the proof, the key step is that you reduce it to this finite subsystem, which I mean, assuming that F is realized by G, then you know that you've got this F sub I realized by G sub I or by G sub I star. And you show that G sub I star has to contain a product of simple groups, and that just there are no simple groups with the right properties, with the right automizers, automorphism groups. And okay, so that, yeah, unfortunately, I mean that this gets nowhere towards doing that. I mean, we always hope that somebody will come up with some property of realizable fusion systems that doesn't hold for all that doesn't hold for all saturated fusion systems, but so far nobody's proposed. Yeah, I think nobody's even proposed a possible thing. Now there is the one exception, These, at the prime 2, the Solomon or Benson-Solomon fusion systems are known to be exotic by Solomon's theorem. So that does not require the classification. It's only at odd primes. All exotic examples we know at odd primes do require it. Now, the union of the Benson-Solomons fusion systems is the fusion system of the Dwyer-Wilkerson group, BDI4. And yeah, that's one of the things in the back of our minds, which we keep forgetting, but it seems very possible that we can prove that it's exotic in this sense. This infinite thing is exotic in this sense without using the classification. We've not tried that yet because there are too many other things to look at. But yeah.
And